Afternoon, everyone. My name is Boyan Kim. Today, I will present my research on building a dual-spectrum image alignment dataset for maritime detection. Looking at maritime footage from RGB and infrared sensors, we face a distinct problem: sensor misalignment due to different field of view and mounting positions. To train our AI on both spectrums simultaneously, we must first mathematically align these images. I will cover four main areas: our motivation, methodology, research, and conclusion. Let's begin with our motivation. Relying on single sensor creates clear blind spots. Visible light or RGB cameras provide excellent high-resolution texture and shape recognition during the day. However, they are highly vulnerable to bad weather conditions such as thick fog and dark light environments. Conversely, infrared sensor can perfectly detect the thermal signals of objects at night or in a bad weather, but they suffer from lower resolution and a complete loss of surface texture and detail shape. Therefore, to ensure robust detection, we need dual spectrum fusion to combine the complementary strengths of both sensors. However, before fusion, we must address spatial alignment. As shown in this error visualization, simply overlaying RGB and IR images causes a severe mismatch. Resolving this is our critical first step. We developed a precision spatial alignment pipeline based on feature point matching. We extract frame, perform pixel mapping so objects' positions and size match perfectly. We perform pixel mapping based on extract feature points so that the position and size of the object match perfectly between the two spectrums. Finally, we perform a channel-level combination, merging the RGB and IR channel into a single aligned dataset. This merged the RGB and IR channels into a single aligned dataset, overcoming scale and position errors so the network can effectively learn complementary features. Next, we process this dataset through our optimized Yellow 11 architecture. We introduce SE, CBIM, and CA attention modules into the backbone to maximize spatial features. To keep the network lightweight yet aggressive for distant objects, we modified the head by connecting a P2 layer with a BiFPN structure and applying ghost comb. Finally, we utilize high convolution 12A pixel inputs. For our closed mosaic training strategy, during the first half of training, we actively use mosaic augmentation to aggressively teach the model complex pattern. In the second half, we disable it. This allows the model to fine-tune on original images that resemble real maritime environment, ensuring robust detection in severe weather. Moving to our quantitative research, our baseline Yellow 11 has achieved an 0.694. Applying ghost comb increased this by 8.2 percentage points, providing high efficiency. Ultimately, our proposed model, utilizing Yellow 11x high-resolution inputs and closed mosaic, achieved an outstanding final score of 89.8%, completely surpassing the previous 76.1% baseline for multispectrum fusion. Qualitatively, our model accurately recognized chip with confidence score over 0.8, even against thick cloud and heavy sea fog where human vision fails. Thanks to the P2 head optimization, it perfectly captures small and distinct ships near the horizon. In conclusion, we achieved three milestones. First, we built a precise, large-scale aligned dataset of over 90,000 images. Second, we designed a customized, lightweight edge AI model optimized for autonomous surface vehicles. Third, we achieved a breakthrough performance of 89% and reaching an optimal speed to accuracy trade-off. Our next step is deploying this model directly onto hardware edge devices for real-time verification in complex environments. Ultimately, this will be laid on the foundation for a flawless enduring maritime surveillance system. Thank you for your listening and attention.